Okay, I'd like to thank the organizers for inviting me here, and this work could be on a path integral approach to computation of entanglement and understanding some properties of non-equilibrium dynamics, mostly in simple systems because this is still in work in progress. And before going on, I should sort of point out that this work is done with my PhD student, Rupayan Ghosh, who is there in the audience, and two collaborators, one Nicolas Dupuy, who is in France, and Arnav Sen, who is my colleague at ICTS Calcutta. That's where I work. So here is a brief outline of the talk. First, I'm going to sort of provide a statement of the problem and motivation. Why do we want to look at these problems in this way? And then develop the formalism a little bit. This would be followed by an application of this formalism where we would show a calculation of entanglement entropy of the Bose-Hubbard model, both with and without presence of artificial gauge fields. And these are relevant cold atom systems where people have looked into several properties, both experimentally and theoretically. And then I'm going to show how this formalism could be applied to non-equilibrium dynamics for relatively simple systems. And one thing that comes out from that application is that one can compute return probability and counting statistics of Gaussian systems in a relatively straightforward manner. And then this would be followed by future directions. And so what we want to do here is to compute the matrix element of the density matrix of fermionic or bosonic systems between two arbitrary coherent states. So that's the first thing that one needs to sort of look at. So of course, because you are taking expectation value of some exponential operator, I mean, a natural choice of doing this is the path integral approach. But once you try to do this, you immediately see that the end states of these path integrals are fixed, and therefore, you cannot write this easily as standard bosonic or fermionic path integrals with periodic and antiperiodic boundary condition, because the boundary conditions are not in your hand anymore. And therefore, what happens is that when you try to do this calculation, you of course expect to get the answer in terms of some correlation functions of of bosons and fermions, but these correlation functions cannot be computed using Matsubara formulation because you don't have this periodic or antiperiodic boundary condition. You cannot really use Matsubara formulation. So the question that we want to ask is that is there a way to express this kind of matrix element in terms of correlators which can be computed using standard Matsubara formulation? Now the question is, why do we ask this question? Okay, so the point is that if you could do this, then the knowledge of rho Fi allows one to compute several things. One of them is the entanglement entropy, and it also allows one to track several boson and fermionic systems with Gaussian action in terms of a single Matsubara Green's function. Because as we'll see, if the action is Gaussian, then only the two-particle Green's function is what is relevant. But this does not mean that this is limited to systems which have a quadratic Hamiltonian, okay? Because we know several systems which might have Gaussian action, but not a quadratic Hamiltonian. One example that we are going to explicitly look at is this Bose-Hubbard model which can be treated within strong coupling mean field theory to give you a Gaussian action, but cannot be expressed in terms of a quadratic Hamiltonian. Spin models in large N limit is probably another example. Now, in addition, the thing is that the knowledge of this rho Fi at a finite temperature, okay, allows one to describe the evolution of a system if you just do a weak rotation. Now, weak rotation, of course, is complicated, but nevertheless, this thing allows you to sort of compute the matrix element of the unitary evolution operator as well. And that's one thing that we are going to look at. And this allows us to track non-equilibrium dynamics in certain cases. We don't need to, so if you do this, you don't need to resort to Keldysh formalism. That doesn't mean that this is simpler and better. It just means that this is a different formulation, because here you have to take a weak rotation, which is not that easy. Okay, so the difficulty lies in there. So let's just look at the formulation. Okay, so what we want to do is to calculate this matrix element, and if you do a simple Suzuki-Trotter decomposition of your path integral, you come up with this standard path integral in discrete time stuff. And you see that these terms, which has this, the final and the initial field configuration, makes this path integral a bit tricky. Except for the field terms which involves these fields, the rest can be expressed in terms of standard path integral. However, as I mentioned, because the states rho f, phi f star and phi I are a priori specified and not to be integrated over, this is not a standard path integral anymore. So the question is, how do you use Matsuburg formulation to in addressing such a problem? The trick that one has is to introduce a new set of fields, lambda and lambda star, and this d phi n star, d phi n, and use this identity. So this identity can be trivially verified by first integrating over the lambda fields, and this just falls out. But once you take this and insert it as an identity in here, because exponential of this factor times this integral is just identity, to insert it here, you find that the last line of this, and do a bit of manipulation, you find that the last line of this can be expressed in terms of a standard periodic or antiperiodic path integral. The price that you pay is that now you have these extra fields, lambda, and which you still need to sort of keep. Okay, so you can trade in these boundary conditions by introducing this new extra fields. So, and then you can symbolically integrate out the phi fields, and you get these generators of this, you get these WNs, which are expectation value of this phi j. But the point is that this correlation function, the multi-body correlation functions, can all be computed using Matsuburg formulation. And that's the good part about this. And finally, if you integrate out the lambda fields, you get this effective action, which gives you the answer for this path integral. And these G's are the correlation functions of the lambda fields with respect to this S prime effective, which is this. Okay. Of course, this can be only done symbolically. I mean, in principle, these higher order correlations are very hard to compute. So what I'm going to do now is to sort of do this for the Gaussian part where the computation is trivial. Okay. So if you had a Gaussian action to begin with, okay, then you could actually do these integrals because everything is Gaussian, and you could just go ahead and do these integrals. And what you find is that the answer can be written in terms of a single Green's function, which is at tau equal to 0 plus. And which is again, this is just the sum over frequency, Matsuburg frequency of this integral. So what it tells you that for this Gaussian action, there is one single Green's function, which is G of 0 plus, which gives you all information about this density matrix element between two arbitrary covariant states. And moreover, one can show, and this is something that we are going to look at, that you can describe the dynamics of the system in terms of this finite temperature using G0 plus. So now let me just try to get into how to compute entanglement using this density matrix element. So there are many ways of doing it, and I'm going to just say something standard, which is already there in the literature. So if you have the density matrix element, you can simply compute the expectation values of the fields, okay? And these are the only non-trivial correlators for a Gaussian system. And then for bosons, you can map it into a bunch of harmonic oscillators and construct the covariance matrix from there, okay? And this is a well-known technology that from this covariance matrix, you consider the which is restricted to this reduced subsystem. So which is where so you take this covariance matrix and you restrict this J and J prime, which are the space levels within the subsystems, and that gives you the covariance matrix corresponding to your reduced density matrix. And from there, because it's a Gaussian system, you can directly read off the von Neumann entanglement entropy. And for fermions, it's even better. You don't need really the pi correlators. You can just do it from this plot. You can also compute the Renai entropies, and there are many ways of doing it. You can directly do it from the path integral. There are methods by Wilczek and others who has done this. But another way of doing this is that if you know the covariance matrix, you can get the entanglement spectrum from there, and the Renai entropies can be directly expressed in terms of this entanglement. So we shall use this formulation to actually calculate the entanglement of the bosons in the Bose-Hubbard model within strong coupling mean field theory when it comes to it. Now, let me try to show why this is important for non-equilibrium dynamics. And here, I'm only going to restrict myself to Gaussian action. So, you see, the quantum dynamics is described by an evolution operator. And this, through a weak rotation, is obviously related to what we just discussed, rho, because you would just need to do a weak rotation t going to minus I beta h for going from real to imaginary time. And because you already know the answer of the matrix element of the density matrix between two coherent states, you also know the answer modulo a weak rotation about density matrix matrix element of the unitary evolution operator between two coherent states. Okay, all you need to do is to know this Green's function and calculate G0 plus from here. If you know this, then, and using our earlier formulation, we could get this, okay, in terms of by solving this, and then we need to rotate back to real time, and that would give you the density matrix element of the unitary evolution operator between two states. Now, the point is that this avoids Keldysh contours. It only requires one of the Keldysh Green's function, which is G greater than in the Keldysh language, which is G0 plus in the Matsubara formulation. But the point is that does not mean that this is simpler, okay? Because here you need to do this weak rotation, and unless you know this Green's function analytically, or you come up with a clever trick of doing it, this is usually very, very hard, at least numerically, doing this weak rotation. So that's the weak point of this method. But for this kind of systems, and in many cases, at least one case that I'm going to demonstrate, this gives an easy way of computation. So let me take a trivial example to demonstrate this point. So suppose I take the simplest possible system, just a single oscillator. Okay, you could take a bunch of unconnected oscillators too. We know that, for that, if I try to calculate the density matrix element, because I know the value expectation of the density matrix in the number basis, I can easily compute its matrix element in the coherent state basis. And the answer is given by this, where f of t is just the integral of this function omega t, and this function omega t with a factor of I. Okay. Now, how do we get this result from our formulation? And that's the standard thing that we do. The first thing to compute is the Green's function corresponding to this Hamiltonian, which in this simple case can be done, and this is the Green's function. So we calculate G0 plus from here, where I put tau to 0 plus and tau prime to 0, which means that only this term survives. And then we just put it back in the formula and we get back the same result. Here we could do the weak rotation exactly because the thing is so simple. But this gives us some confidence that there is at least some simple systems where this can be done and it gives the right result, and this is just a check. So now let me try to calculate the entanglement of the Bose-Hubbard model. And okay, so let me try to introduce this a little bit. So we all know about this Bose-Hubbard model and its application in cold atoms. So what you do is that you essentially trap atoms and put an optical lattice. And for deep enough optical lattice, the hopping strength of this bosons from one lattice to another is small compared to the on-site interaction between the bosons. And then they get into a mode state, and if you decrease your hopping, it goes into a superfluid state, and thereby giving us the mode insulated to superfluid transition. A model Hamiltonian, which is widely used to describe this kind of system, is basically the Bose-Hubbard model, which has the hopping term out here and the on-site interaction, and of course we work in the grand canonical ensemble, so I put in a chemical potential. So it's really the ratio of mu over u and t over u, which determines the phase diagram. And that's a very well-known phase diagram, has been treated in many different approximations, and also using exact quantum Monte Carlo. So we pretty much know all that. But in a earlier work, quite a few years back, so me and Nicola, we tried to describe this in terms of path integrals. So what we do is that we write down the coherent state path integral for these bosons, and then decouple the hopping term, which is the weaker term in the mod phase and also near the transition, using a Hubbard-Stratonovich field. And this allows us to generate an effective action However, this effective action, if you just decouple it once, it turns out that this effective action is described in terms of fields phi, which does not have any simple relation to the boson fields, the original boson fields. Okay, and that is seen by trying to, if you, for example, if you try to take the limit, hopping goes to 0 and try to describe the Mott limit, you will get a completely wrong answer from here. The trick, therefore, which we did is to introduce a second Hubbard-Stratonovich field and to write things in terms of another field psi. And if you can show, and that's why we do this, is that the second Hubbard-Stratonovich field has exactly the same correlation function of the original boson fields. And that's why the effective action in terms of it gives you a much more sensible effective action in some sense. And one can show that this effective action has a Gaussian part, which is this, and a quartic part. But the Gaussian part already has effect of interaction through this local Green's function G0, which is given by this quantity. Okay, that's the on-site Green's function. That would be the only Green's function if you didn't have hopping. So that's the exact Green's function in the Mott limit. So these two Hubbard-Stratonovich transformation essentially amounts to a partial resummation of the interaction process. This was shown by Friedrichs and HRK, who is sitting here, and others. They of course went much beyond this simple procedure, but I'm going to just take this. Okay. So what you can do then, because you now have a description of the Green's function, you can think of decoupling this interaction term using mean field theory. In the Mott phase, this mean field is 0, and your Green's function is just the quadratic Green's function. And you can get this momentum distribution of the bosons using this, and it shows all the right traits. For example, as you approach the transition, it essentially shows the precursor peak that the bosons tries to flock in the k equal to 0. You can also approach the superfluid phase where you decouple the quartic term by some mean field, and there you get these 2x2 actions, the mean field action, and you can find out the spectrum. Now, one interesting part about this is that the spectrum consists both gapless and gapped modes, the so-called Goldstone and the Higgs mode, which you find from this approach. And the gapped modes are significant spectral weight if you deviate from k equal to 0 point. Okay. Now, this is going to be important when we compute the entanglement spectrum. That's the entanglement or the von Neumann entropy. That's because you see here we are doing we're trying to get things in terms of real space correlation functions, which is a sum over all momentum modes. And therefore, if you have contribution at some higher k from modes which are the gap modes, that is going to shape the nature of your entanglement as well. Okay, and that's what we see also. So okay, so what we do now is that we take this Gaussian action, this mean field in the superfluid phase or just the Gaussian part in the Mott phase, and we use our approach, which I just described, to compute the von Neumann and the Renai entropies. Okay, I'm going to show you results only for von Neumann and von Neumann entropy, but Renai entropies are similar. But before that, one thing that I would like to point out is that the same formulation, okay, so there is some experimental stuff that was done by Spillman's group, and there was some theory. But the point is that the good part about this method is that it allows you to address systems where you have either abelian or a non-abelian gauge fields. Because what happens is that in presence of such gauge fields, your hopping matrix gets changed because it has additional phase factors. But that's relatively straightforward to incorporate in this formulation. All that happens at the end of the day, you turn the crank, and when the dust settles, what happens is that instead of a single hopping parameter, you end up with a hopping matrix. This Q essentially comes from the amount of flux that you put in through each placket. That's the sort of like the strength of the magnetic field. And the whole thing now becomes a Q by Q matrix because it breaks down into magnetic Brillouin zones. So if you put a flux of 2 pi over Q through each placket, then your system breaks down into a Q by Q magnetic Brillouin zone. So you can again compute the poles of the Green's function, and this is just in the Mott phase. And the density from the momentum distribution function, you again see precursor peaks, but these peaks now occur at different momenta, which is now controlled by the strength of this vector potential or the magnetic field that you put. So we are also going to look at the entanglement. Again, we are going to use this Gaussian Green's function and do stuff with that. So let me just give you the result for the entanglement calculation. The technology is the same that I have described before, but so what we find is that the entanglement computed in this way from here satisfies the standard area law, which is reassuring. And then in the superfluid phase, it has an additional subleading term, which is a coefficient b times log L over A. And this b for a system with just gapless degree of freedom is supposed to be a universal constant. But here we don't find this to be an universal constant. It varies as a function of the hopping parameter, and that is expected because the system knows that this phase does not just have the gapless modes, but it also had the gap modes. And therefore, as you change j over u over several values of the hopping parameter, this b will change. So we also compute the von Neumann entropy using for systems with abelian and non-abelian gauge field. And one of the things that we see is that when you increase the strength of these fields, the system gets more entangled, and that is to be expected because you develop more correlations. Because the bosons essentially move not just to k equal to 0, but with other k's, and therefore more correlations develop in these systems. The system gets more entangled. So now let me switch gear and come to the periodic dynamics of Dirac fermions. That's another application of this example. So here what we do is that we take Dirac fermions in d dimensions, such as which is relevant for Kitaev model, Ising model in d equal to 1, Kitaev in d equal to 2, and quasi-particles in graphene and topological surfaces at d equal to 2, also for Weil fermions if you go to d equal to 3. And essentially it's a 2 by 2 matrix with some diagonal and off-diagonal terms. And we are going to drive this system periodically using a square pulse protocol, which is convenient for our calculation. And so what we do here is that we take this system, and for any constant g, it's very easy to calculate this g0 plus, because for each half of the square pulse, it's just a constant Hamiltonian, evolution by a constant Hamiltonian. You do this, and then you compute the density matrix expectation value, from which you can get this expectation value of the unitary evolution operator. And that's a Gaussian of this form, where L is a matrix which you can which is given by this. Okay? Now, once you have this, you still need to get the evolution operator expectation value for the entire cycle. So there what you do is that you use the fact that this is Gaussian, and therefore you can simply do a Gaussian path integral to get this, and the answer is just the product of these two. Okay, so it's really that simple. And this is just non-interactive. Yeah, as of now it's just non-interactive. So what happens then is that, so what is reassuring is that if you take these matrix elements, and I'm not going to show you the entire algebra, you get back the old result for the Fluke energies, which are known. So this gives you some confidence that this method actually produces the right results in this. And then using this, we are going to compute two different things. One is the counting statistics, one is the return probability of these driven fermions. So what we say that we start with a number state, which is of this form, okay. So this is the number of electrons, and this n of minus k in our formulation is the number of holes, okay. We start with this number state, and we want to find out that after evolution by a time t, what's the probability of that state to return to itself, okay. That's called the return probability. And it turns out that because you can express u as in terms of, the matrix element of u in terms of these coherent states, and the overlap of a number state with this coherent state, you can express the whole thing as a Gaussian path integral. And you can just evaluate this. I mean, that's relatively straightforward. So if you have a starting state like this, what you find is that the the answer is given in terms of the eigenvalues and eigenvectors of the Fluke Hamiltonian. So this directly relates the eigenvalues and eigenvectors of the Fluke Hamiltonian with the return probability, and we compute it for several drive protocols. Now, one of the interesting things which is probably to be expected is that once you take the amplitude of the drive such that you go from one phase to another through the Ising transition, this is for the Ising model, you find that the return probability drops sharply, but that I guess is only to be expected because the phase changes and system find it's more difficult to sort of come back to the. Finally, we do the characteristic function of or the counting statistics, and this is so okay. So the counting statistics, it involves probability distribution of an operator O, which is related to its characteristic function. Okay, so that's the definition. And this characteristic function can be written in terms of, well, at 0 temperature, it can be written in terms of this unitary evolution operator. So again, if we start from a number state, you see, I haven't done much. All I have done is to give myself a more difficult task of computing a slightly more complicated path integral. Because I know the matrix element of U and U dagger between coherent states, and the only task is to sort of know the matrix element of this operator, e to the power IFO, between the coherent states, and then I can express everything in terms of the path integral. And this is not so difficult to compute. I mean, it turns out that if you have a number operator or the order parameter, which is this off-diagonal operators, you can essentially compute this O in K. And this is in the basis of Nk and N minus K, I mean, electron hole basis. So wave functions are two-component wave function. And then you do this calculation, all you find is that there are, again, some Gaussian path integrals, and the answer comes in terms of the matrix element of the Fluke Hamiltonian. If not, Fk naught is just a parameter, which is your choice, that's there in this characteristic function, but the rest of it is completely determined by the matrix element of the Fluke Hamiltonian. And this tells you that, this method gives you an easy way of relating things like counting statistics and return probability in terms of the Fluke Hamiltonian of the problem. And you can not only do this for density operator, but also for the off-diagonal operator and for any state. And here is a plot, and this is also kind of expected in the sense that when your time period is large, which means you're driving at small frequency, the Fluke Hamiltonian develops multiple oscillations, which shows up in this, in this plot out here. So your characteristic function mimics that property. And this is true for both for density and order parameter operators. So the idea is that this allows us some analytical handle on this kind of quantities, which is what I wanted to show. So let me try to conclude. Probably finishing well before time, but that's good. So what we have done is to develop a path integral method for computing matrix element of density matrix of many-body systems in terms of Matsubara correlation function. And we have applied that only to systems with Gaussian actions. This allows us to address entanglement and non-equilibrium dynamics of a class of many-body systems with Gaussian actions, and maybe applied for computing entanglement measures of strongly correlated Bose-Hubbard model within strong coupling mean field, and there are other models where this could be useful. The point is that there are future directions, and things like Luttinger liquid and large N models where you could have, it's easy to develop at least perturbative schemes for to do this kind of calculations. Those would be the next things to do. And those are our future goals. So I think I'll stop here and thank you for your attention.
Yeah, thank you very much. So we have time for discussion.
Yeah. Right. No, this is general because you see, if the weak rotation can be done exactly, then I haven't made any approximation. If the system has Gaussian action, this is completely general.
I mean, usually you start with an initial condition. I mean, I understand your it will
No,
become
but
e
I'm
to the power
calculating
IHD.
the matrix element of an operator between two arbitrary coherent states.
So in that case, it will be a dynamic starting from a coherent state, because that's what your
No,
initial.
I'm just calculating the matrix element, and then if you apply that evolution operator to sort of address the dynamics, then of course, it depends on what you start with.
No, I'm saying you are calculating, for example, entanglement entropy. This would be entanglement entropy of what non-equilibrium dynamics?
No, the entanglement entropy, for example, is done for an equilibrium system, okay, ground state equilibrium stuff. These are two separate things. All I'm saying is that the method gives both, but these are two separate blocks. We haven't really connected them.
Okay, thanks.
Back to Hubbard-Stratonovich. This one? Yeah.
How you deal with the second part? You said that.
Oh, we just decouple it using mean field. The mean field is 0 in the Mott phase, and it is finite in the superfluid.
Yeah.
That's why it's a strong coupling mean field theory. I think HRK went much further than this, and he resumed processes which are not here, and you should really talk to him.
Ask an elementary question. So why is it advantageous to use coherent state basis in computation of entanglement entropy? Is it always advantageous to use this?
No, it's not always advantageous. The only thing is that here, you see, what I have is an effective action which has a Gaussian form, right? But you will also see from the structure of this G inverse that it's impossible to write this as a Hamiltonian, local Hamiltonian, which is quadratic. But if I know how to sort of get entanglement from a Gaussian action, then I can use the correlation function technology to get the entanglement, but I cannot do it from the Hamiltonian. That's why I use this here.
So then this approach is limited to sort of mean field treatment of it.
Mean field, large N, for Luttinger liquid, maybe you can do something. So beyond that, it's developing perturbation schemes, and we are thinking about this, but we don't really know yet.
Okay, if not, let's thank the speaker again.
Thank you.